here's what's nice about it. I can come here now and say, oh, so if I'm just going to do this step, I'll do leapfrog. And over here, I can do Euler, right? So now you have very quick, clear steps of what you would take that work well here, and in fact, you can calculate CFL conditions exactly for these two steps, whereas here, they're all mixed together, and now one of the terms would suggest using leapfrog, one would suggest using Euler, and they're both incompatible essentially with the other term. Here, I just get around that altogether. Yeah?
No matter which one we start with, can we start with the diffusion and put the result from that into the heat equation and then do the loop?
Yeah, it doesn't matter. Yeah, we could have done diffusion first, this second. In fact, we'll come to that in a minute, and I just lost my place because I was fooling around with my fingers on the board here on my iPad. Okay, I'm almost back to where I was. There, okay. So this is the idea, and there's some reasons you might want to do this, besides the fact that now you can take your terms, that you take methods that you know will work. Okay? So for instance, this might come in handy also in the problem we've already considered. Right? When we think about what we did in homework 4, what we are thinking about is then separating in terms of the physics of the problem, right? This is kind of really the underlying principle here, is to say operator splitting allows you to split different types of physics. And what the splitting physics means is different kinds of mathematical solutions, right? And so you can think about, well, I could do a step, for instance, like this. Why do I do this step? Because this is waves. That's wave behavior right there. And maybe what I really want to do is to really capture very nicely wave behavior. There are stepping routines that are ideally suited for wave behavior. Euler is not one of them. Leapfrog is. So if I want to take as big a step as possible, right? Ultimately, my goal is to take as big a delta t as possible. That's always going to be your goal. How big can I take delta t and still be accurate? Okay? So the bigger the delta t, the faster your code goes. Period. How big can I take it? Well, you know what? If you make use of good schemes that are especially suited for waves, you're going to be able to take a bigger delta t. So here, you say, I've separated the wave dynamics from the other piece, which is the diffusion dynamics. Okay? And this is diffusion. And schemes that do this nicely are very different than schemes that do this nicely. Here, by separating it, you can basically use the best scheme for this and the best scheme for this, because the best scheme would be incompatible for both at the same time. Okay? That is the idea behind operator splitting. Okay? And so you take a delta t amount of this, a delta t amount of this, and now you say, well, if I take a delta t amount of this, and then a delta t amount of that, effectively I've taken a delta t amount of both, and I've gotten my solution to the future. Okay? Everybody good with that? Does that make sense? All right. So let me make a couple of the comments about how else this can be very useful. This hits a little closer to home for me. I'm going to tell you about one problem I look at quite a bit. It's called the nonlinear Schrodinger. And here it is. Okay? So normally the Schrodinger equation is just this here. It's called the Schrodinger here. So it's kind of basically, how did Schrodinger come up with it? Well, Schrodinger was playing around with, okay, we knew the quantum mechanics, there was some wave behavior there. Right? So they started talking. De Broglie said, hey, look, it's like a wave. Yeah, but guess what? You can't know its position and its speed at the same time. Okay? Heisenberg said there's this uncertainty. Well, crap. If you're a wave equation, Normally, you'd specify both position and velocity of a wave initially. You can't do that. You need a wave equation that only has one initial condition. This is the simplest wave equation that has one initial condition. That's how Schrodinger wrote it down. It wasn't like anything that fancy, although we think about it. And then people justified it later in life, right? So Schrodinger, in fact, how this comes up as a minimization principle wasn't even proved till, I think, 2008 or 9. Okay, so he wrote this down in the 20s. He said, I just want a wave equation with one initial condition. There it is. Foundations of quantum mechanics. Hey, I built my iPhone off of this, by the way. Right? I didn't build it, actually. Someone did. But that's really, someone built an iPhone off of this concept, right? So this is how it works out. Now, nonlinear Schrodinger here, normally there's a potential here. This potential is itself. So it depends nonlinear on you. Okay. So in this case, it's not like there's an I here. Yes? Yeah, because I have one time derivative. So I specify the initial. Usually you would specify this thing at time t equals 0. In a normal wave equation, ut equals uxx, something like this, you would specify, what's that? UTT. This is a one-way wave equation, which is not what was observed in quantum. Waves can propagate either direction. That's what happens here. Two derivatives requires two initial conditions. Yeah. Yeah. Okay, so we have this. Now, the interesting thing here is, because of the I, this term here corresponds to dispersion. So you know all about dispersion. I'm going to try to do this with a black marker. Check it out. You'll see what I'm talking about. That's right. Pink Floyd album cover, 1970s. That was when they first discovered what prisms do. Okay? Pink Floyd. They were scientists, mad scientists. Anyway, we know this effect here. Basically, what this means is different frequencies travel at different different frequency or different wavelengths travel at different speeds. Okay? So what you get is, if you have a packet of information, quantum information, if you look at this Fourier transform, it has a spread in the frequency domain, and what it does is every one of those frequency components travels at a different speed. So in time, what's going to happen? This thing here just starts to spread out because they're all traveling at different speed. It's this effect here. It's like a prism. Okay. So that's one effect. This here is called a self-focusing effect. If you take this out, this here basically starts inducing a nonlinear phase change. And the way that people oftentimes think about this is, this nonlinear phase change also can create what's called a self-focusing effect. So I'm just going to hand wave this a little bit here and tell you why this is an important equation. This term here wants to take a packet or a pulse and spread it out. This term here would like to compress a pulse. If I can make this just right so that the compression and the spreading are balanced, then I get what's called a soliton. Okay, it's a perfect balance between nonlinearity and linearity, and you get these waves that travel forever. So, in fact, this was proposed as a way to do optical communications in fiber, among other things, and it's so popular. Do you remember there was a Star Trek episode where there was a soliton going to go destroy a planet, this big soliton wave, and Geordi figured out that if you threw a big torpedo at it, one of those light torpedoes, boom, it blew it up, and it stopped the soliton. No way. But anyway, they saved the planet as usual. Okay. So this is not like, it's not so different as, I'm going to propose using split step here for a very specific reason. If you start thinking about it, it's not like these two effects. Both these two effects are having phase changes. So it's not like the case of wave propagation and diffusion, which are completely different phenomena. I'm going to propose using split step here for a very different reason, which is, altogether, the solution to this technique, the solution method for this problem is actually pretty sophisticated to do this problem. However, if I actually look at them in pieces, they're pretty easy. So for instance, think about what I got here. Let's think about the first part, which is just, let's just ignore that nonlinear term and look at something like this. This is just dispersion. The nice thing is I can solve this very nicely using Fourier transforms. Okay? So if I Fourier transform both sides with respect to x, right? Here I get a minus k squared, right? Oops. Right? So then I have so far so good. Was that? I put it over here and I multiply by negative I. Yep. Okay. So, and this is just a simple first order differential equation, right? Solution is u hat is equal to e to the minus I k squared over 2 t times whatever the initial condition is. Okay. In other words, if I want to solve this over some delta t, all I got to do is take my initial condition, multiply by that factor, inverse Fourier transform it. And in fact, if I know what the Fourier transform of the initial condition is, suppose I put in a Gaussian or something nice like this, I could actually compute this exactly. But even if I don't, over any delta t, I don't have to solve this thing anymore. In other words, notice what I've done here. I do not have, this here, when we Fourier transform, I could say, let's put this into OD45, and then have OD45 step forward into the future. I don't need to do that. I have a solution right there. All I got to do is take my initial condition, Fourier transform it, multiply it by this, inverse Fourier transform. No OD45 required. Okay? So it's pretty nice. Effectively, it's like having an exact solution. So great. That's half of the problem, right?